Hello everybody, welcome back to the lecture on Polymer Science and Processing. This week's lecture will be the last on the chemistry part of this set of lectures, and I will introduce a few other polymerization techniques to you. Before we do this, let us briefly recap what we learned last week. We talked about free radical polymerization, which is one of the key polymerization techniques that leads to a lot of polymers, from everyday life, such as polyethylene or polystyrene, and so on and so forth. And the idea was that we use a very active species, which in this case was a radical, and we let this react with monomers that have a double bond. And in this case, we create, while the radical attacks the double bond, it creates a very high energetic species. So the radical is transferred from the initiator to the monomer, and then it jumps through the monomers really quickly. And this chain reaction, hence the name chain polymerization, leads to the formation of polymers really quickly. Remember the analogy we took of putting a hot ball into, let's say, a football stadium, and a lot of people touch it. Nobody wants to touch it for a long time because you get your hands burned and eventually somebody drops it. This would be the termination. So the key concept is really at the very beginning you already form long polymer chains, and this goes on and on until all the monomer is consumed, or maybe until the initiator runs out. So what I want to discuss with you today is, as I said, a few other polymerization techniques, and we will start with thinking about what other active species we can use, or what other high energy species we can use to force a polymerization. So what you will see is we will talk about cationic and anionic polymerization, and then we will come to a bit more specialized classes like living polymerization and a short introduction into catalysis for polymerization. But let's first consider the following point. So we have active species, and what we learned is last time for a radical, we have our initiator that carries a radical. We let this react with a vinyl monomer carrying a double bond, and then this forms a radical species. And this now is the propagating unit that keeps propagating more and more. So we will form a polymer. So if we look at this scenario, clearly a radical has an unpaired electron, which is not an energetically very stable situation. So it is yearning to find a double bond so it can recombine to form a sigma bond, and then the radical is transferred to another position. Now, if we think about what kind of other species we could use that are active and would like to change their high energy to equilibrate in a polymerization, we could easily think about two scenarios. Either we take another electron away, then we wouldn't have any electrons here and would have a positively charged carbon atom, or we add another electron and we would gain a negatively charged carbon here. So we could conceptually think about a scenario that looks like this, and now there's no electron here at all, and this is what we call a carbocation. Or we add one more electron into this orbital, and then we form a species that has two electrons here and is negatively charged. This we call a carbanion. Now we all know that carbon is neither extremely electropositive nor extremely electronegative, somewhat in the middle ground, so it will not have a strong tendency to like getting electrons taken away from it, nor does it like to have a lot of electrons. Now this would be a typical anion, something electronegative, and typical cation would be something electropositive, like sodium plus or so. These species are not very stable because the carbon is not very happy with either scenario. And in fact, they're actually very reactive. And in order to create something like this, we need to tailor our monomer situation here in a way that we can support this a little bit. So what we need to do in order to stabilize something like this, we need to choose groups here that can donate electrons. In chemistry, this is called a plus I, an inductive effect, or a plus M effect, a mesomeric effect. And that means that these side groups here, what I denote X, need to be able to push electrons onto this carbon atom in order to make it a little bit easier if you want to carry this positively charged, so to mitigate this lack of electrons here. And an example for this would be a monomer with a double bond that has, for example, two CH3 groups. Here we see, of course, the carbon has the same electronegativity as the central carbon here, but this is surrounded by three hydrogen atoms that are even more electropositive. So they will shift electron density to the carbon, and all in all, electron density will therefore be increased here, and this can shift electron density onto this central carbon. So we need to increase the electron density as this carbon. And likewise, if we do the same thing for the carb anion, this also needs to be stabilized. And now we require the inverse effect. We need to have groups that can draw electrons away from the central carbon. So again, in chemistry, we speak of a minus I, an inductive effect that draws electrons away, or a minus M effect, a mesomeric effect that draws electrons away. And as an example here, we can think about a monomer that, for example, looks like this. And in this case, we can have electrons that are sitting here, can move around, this is maybe a bit easier to see if we already take the active species here. So that's the negative group here. So if you have a negative charge here, this negative charge can be delocalized over this entire molecule here and all the way up to this carbon atom. And this, of course, stabilizes the situation because the electrons don't sit exclusively here, but are somewhat distributed around. Okay, so these monomers, these are the requirements to generally use ions to initiate a polymerization or to use ions as an active species. Maybe just as one thing, we have a special case. Styrene works in both ways. So styrene, let me just put this here, can have with a positive charge, the electrons in the ring can move out and delocalize the positive charge. Which now sits in the ring, and then likewise this positive charge can jump around in the ring, so it could also be here or it could also be here, similar to what we discussed last week, or 2 weeks ago. So this would be one possibility for a styrene molecule to mitigate a positive charge here. And similarly, if we have a negative, put it again, initiator, so then this can attack here and we will form a carb anion. In this case, now the electrons can go into this bond connecting the ring, and this will make space here. So as a mesomeric stabilization, we get a scenario where now the negative charge is within the ring, and within the ring, again, it can propagate here and here as well. So the negative charge as well as the positive charge can be distributed throughout this aromatic ring. Okay, so much as an introduction, what kind of active species we can use. Let me just show you a bit more of an exhaustive list on monomers that we can use. Again, you see here, we need stabilizing substituents. And here you see a list of possible monomers for cationic polymerizations. And you see, if you now maybe hit stop and look at each of these monomers and try to figure out why the electron density at the central carbon is increased, you will see there's mechanisms for all of these to get more electrons to the central carbon. Similarly, in the anionic polymerization, we need substituents that decrease the electron density, and you see very typically you have these acrylates here and here. You can have cyanogroups that draw electrons because the nitrogen is much more electronegative compared to the carbon. And as I just showed you, the benzene ring is a good candidate to stabilize both negative and positive charges. Okay, with this, I just want to briefly show you how this process would now work, and we will start with the cationic polymerization. And for this, let me move back to the blackboard. So in order to do a cationic polymerization, we first need to come up with an initiator. And this initiator needs to be sufficiently aggressive, if you want, or sufficiently reactive to be able to force a positive charge into one of these double bonds. Now keep in mind, we form a high energetic species, so we need to create something that doesn't like to have a positive charge even less than the monomer. So we really need to force the reaction to form this carbocation. And in order to do this, we need to create what is known as an electrophile. So something that really wants to attract the electrons of the double bond. And one option is the following. We let aluminum chloride, which is a Lewis base, react with an organic halide compound. So this can form a complex and bind the chloride. And if it binds the chloride, it leaves this organic rest here without its electrons. So this could then depict as an R+. And this complex anion aluminium tetrachloride. So here you see now we have an organic alkyl chain typically that is lacking its electrons, and of course this is also very reactive. Now this is something that will start to burn, for example, if it gets in contact with oxygen, just in an attempt to get its electrons back. So here, now we need to be careful, but now we can let it react with a monomer. Another option, by the way, is bore trifluoride, which we can let react with water. And then we create H+, BF4OH, minus, and now we have here a very active proton if you want. And then we let the entire thing propagate. So now we unleash our active species onto our monomer. So here is the active species that we just formed, and we let it react with a suitable monomer, for example, one that contains two CH3 groups here, as we just discussed before. And now this really wants to have electrons, and the electrons can come from the double bond, and we transfer the active carbocation to this carbon here in alpha position next to the substituents. And here we have our active species on the monomer, and now what will happen is that this keeps reacting more and more. This can attack another monomer, and then we will form and so on and so forth, and then we find our repeat unit, and this is what it will look like. So this is the polymerization reaction. And again here we have our counter ion. Now the question is, how can such a reaction terminate? Now what you clearly see in radical polymerization, the typical elimination or termination reaction was two radicals finding each other. We have two unpaired electrons, they simply pair to form a sigma bond. Now here this is not possible because the active species is an ion, and if you find two ions of like charge, they will repel each other. So the polymers themselves cannot join together and undergo a chemical bond, not because of their like charges. However, in the case of cationic polymerization, there is another way on how to mitigate, or how the system can mitigate this problem. And this is simply by kicking out a proton. So let me show this to you. So we have our polymer here. We have a CH2 group, which is this one here. And then we have our active center and our counter ion. Let me just call it A- for anion. And now, if this bond is used to form a double bond, we can eliminate the positive charge here, and what is left is a proton, which we know is a stable species. We know that hydrogen is less electronegative than carbon, so it will have no problems, or let's say little problems, to leave here and leave the binding electrons at the carbon. If the binding electrons are here, it can form a double bond, and there we go. Then the polymer is terminated. So now this proton is gone. We have our two rests here, and we release a proton, which can exist if you want as a salt, or can bind to the anion here. And after all, now this polymer here is terminated. It doesn't carry an active species anymore. However, it still has a double bond, so potentially it can be re-initiated by the attack of another carbocation. But generally, this is a possibility for such an ionic polymerization to end. So now you would think, okay, why bother? And matter of factly, the cationic polymerization is not used that often. Let me just give you a few examples. So this is what we discussed here. And you see that very often there is a few examples where you can form, for example, elastomers, adhesives, and so on. And often these things are used to polymerize short rings. For example, trioxane or THF, they can be cationically forced to open its ring, and then they propagate more and more. And this is something that we can maybe discuss a little bit in the exercise, but I do not want to dwell into details here. Important for us is that we can use a cation to actually initiate the polymerization. Now we will move to something that is, at least in my opinion, slightly more interesting. We swap the scenario, and now we don't want to use a cation to initiate the polymerization, but an anion. And in order to do this, I will simply make space, and you can already think what kind of a species would be required to initiate a reaction that should propagate via a anion. So what do we need to do to force these molecules to exact a negative charge? Okay, so now anionic So what we need to provide is something that is very nucleophilic, or something that has a lot of electrons that can be forced to give these electrons onto the double bond. And materials that contain a lot of electrons, we typically call bases. So we need a very strong So this can be, for example, if we deprotonate ammonia. So this is a very strong inorganic base, and this can dissociate in a potassium ion and this NH2 minus anion. So you can imagine that this actually has two free electron pairs. This nitrogen really wants to undergo a reaction to bind here. So this is really a strong organic base. This is how anionic polymerization was discovered. The more important one would be, at least in my opinion, organometallic. So an organometallic compounds is, for example, butyl lithium. So we know that lithium is the most electropositive element that exists. So this will be very strongly partially positive, meaning that the binding electrons are all shifted to this butyl chain. And matter of fact, the difference is so strong, which is very rare for a carbon component because it's not per se very electronegative. But if you give it the right electropositive partner, it doesn't have any possibility but to accept the binding electrons. So you could almost write this as butyl minus Li plus. So this is how it reacts. And here you see, similar to before, where we had an organic rest, an alkyl chain that has a positively charged. Now we have an organic rest, in this case a butyl chain, that is negatively charged. And similar to before, butyl actually doesn't really like to be negatively charged. It would rather exchange this negative charge for a hydrogen atom to become butane, and this is why it reacts very violently. So it will try to abstract a proton from wherever it can find. It's a very exothermic reaction. You create butane, which is very flammable, and this means that this entire thing starts to burn very easily. So if this gets in contact with air, it will immediately start to burn. So if you have this in a syringe, you shoot it out, it directly goes into flames. So it's really a delicate component that needs to be handled with care, but nevertheless, you can A, synthesize this, and B, if you're careful, you can handle this, and then you can do something very fascinating. You can put this into a solution of monomer that has the appropriate conditions, namely that it has electron withdrawing substituents so that it can undergo anionic polymerization as we discussed before. So let's see how this looks like. So in our propagation reaction, we let react this butyl lithium that is negatively charged, more positively charged here. We let it react with a monomer, and this X again is electron withdrawing. So now the negative charge here will attack the double bond will flip open and form this carb anion. And then we create butyl, our active species, which is the carb anion. And of course, should not forget our lithium, which is positively charged and kind of sticks around. So now this is of course not the end. Now it can continue to react with more monomers. And it will do the same that all monomers do. It will just do the same reaction over and over again. So now this is equally reactive. It will attack this double bond. This double bond will flip open and we form our first reaction, and now we do this over and over and over again. Sorry, shouldn't forget the cation. And if we do this over and over again, then we will form our polymer, which will have the generic form so this will be a polymer that is formed via an anionic polymerization. So now to the last step of the polymerization, termination reaction. So now let's all think very carefully, how can such a polymer terminate? This is the scenario, and inherently, if you think about the other polymerization reactions that we discussed, there's two options to terminate. One is that the active chain ends meet and recombine, such as in radical polymerization, which unfortunately is not possible here because we have two negative charges. Negative charges repel each other and we cannot recombine them. So we have no recombination. What happened in the cationic case? In the cationic case, we had two hydrogens here. The hydrogens could leave as a proton and would leave the binding electrons here. In this case, the scenario would be exactly the other way around. We already have enough electrons here and we need to get rid of electrons. So in order to terminate this reaction, the double bond or this negative charge would need to form a double bond. And in order to do this, one of these binding partners would need to leave with the binding electrons. So kind of like this. And of course, this is not possible because the hydrogen is electropositive. So it doesn't have any incentive to take the binding electrons with it. It can leave as a proton, no problem. It cannot leave as it doesn't want to leave as a hydride anion because it's too electropositive. So let's directly eliminate this again and simply state here no H minus, and I put an exclamation mark. So an H minus can also not be eliminated from the polymer chain because of electronegativity considerations. And that means we're running out of options. So long story short, even after careful thinking, we cannot think about a way how this chain by itself can relax its state. So there's no termination reaction. And let me specify this a little bit more. We have no inherent termination reaction. Now this is of course a curious, and if you ask me, a wonderful case, because now we have a polymer that doesn't die or doesn't terminate by itself. And what next we're going to discuss is what kind of consequences this has for our polymeric architectures that we can obtain. But before doing this, let me just show you why I added inherent termination here. So of course what we can do is we can force a termination. And this forced termination we typically call a deactivation reaction. So we deactivate the negative charge. But we need to do something for it. And I will give you one example. Very general, this strategy, if we need to, or if we want to deactivate, we add an addition of a reaction partner. So as an example, we have our polymer. And our counter ion here. And now we purposefully add carbon dioxide. To the reaction mixture. Now take a second and think about it for yourself, what will happen in this scenario. Well, we have something that is very electronegative because it has a negative charge. No, free electron pair. Misleading. And we have a situation here in this carbon dioxide where the central carbon lacks electrons. No, it's being pulled in this direction and it's being pulled in this direction, so there's little electron density at the central carbon. Therefore, it is susceptible to a nucleophilic attack by this carb anion. And what we gain by this is a CH2, CR. Whatever these are. And now, if we attack here, one of these bonds will need to open up. Suddenly we have incorporated this carbon dioxide into our polymer chain. And if you look carefully, then this will look very familiar to anybody that is at least vaguely familiar with organic chemistry. This is nothing else than the salt of a carboxylic acid. And if we now add a little bit of proton, HCl for example, or any other type of sulfuric acid, H2SO4 or whatever, so any type of protons, then we can protonate the carboxylic acid, just to show you, then it will maybe even look more familiar. We will form the lithium salt of whatever the anion of the acid is, and the proton will go into the acrylic acid, and now we into the carboxylic acid, and now we created a polymer that has an end functionality in this case with a carboxylic acid. That really shouldn't be underestimated, this possibility to purposefully introduce reactive functional moieties at the end of the polymer chain. Because here we have a very long polymer chain. Oh, this can be hundreds and hundreds of molecules, maybe thousands of molecules. And we only have the carboxylic acid at its very end. Okay, so now the polymer is dead, but we gained a functional group from this. And this is what is called end group functionalizations. If you think a little bit about this, there's also different possibilities for reaction partners that can introduce different groups, alcohol groups, and so on. I do not want to tread into details here, just show you at this very simple functionality how this actually works. Okay, so now you see, yes, we can terminate the reaction, but we don't have to. And this brings me to the next topic, which is how we should interpret this finding. If we have the possibility of a polymer that does not terminate by itself, then we can continue to do things with it. And this is known as a living polymerization. Living simply because there's no termination reaction. So let's look at the properties of such a reaction. But before, I'll clean up again. So now, what does this mean? So first of all, anionic polymerization leads to this living characteristics, as we discussed, because there is no inherent termination reaction. And that means that the polymerization can go on and on and on as long as there's polymers present. So what does this mean? Firstly, I add a certain amount of monomer, X, then I polymerize it, and all the monomers will be added to the molecular weight. Because the polymer doesn't die. Then if I add more of these monomers, it will still continue to grow more and more. And that means we have a very good control of molecular weight because because all the monomer is added at the same time. No? Secondly, our initiator is very reactive. So it will start as soon as we inject this butyllithium into our reaction mixture, it will start to polymerize. That means that the polymerization starts at the same time. Polymers start to form at the same time. And since they don't die, they continue to grow as long as we feed them monomers. And this means that not only do we have a good control of the molecular weight, we also have a very narrow distribution of molecular weight. Now, similar to nucleation and growth phenomena, we nucleate very rapidly. All the polymers start to grow at the same time. And on average, of course, the reactivity of each of these polymer chains or each of these active polymer ends is the same. So on average, they will add monomers with the same speed. And that means that their chain length over time will be similar or will be very, at least, close. And that means we have a very narrow MV molecular weight or a very low polydispersity index, which, if you remember our very first lecture, is the ratio of the weight average molecular weight divided by the number average molecular weight. And you can imagine, since all properties of a polymer depends on, or a lot of properties of polymers depend on the chain length, this is the perfect tool to really investigate these structure property relations. Now, we can make polymers with defined molecular weights. We can also have a very good control of this molecular weight, and that means we can study how this molecular weight influences the product properties. One additional consequence, of course, is if we can keep adding more and more monomers, we can make the chains very long. Which is even better if we want to study such effects. And just to show you how important this control is, or how this really plays out in this diagram that we had, where we plot our conversion P, or if you want time T of the reaction, against the degree of polymerization. Now remember, this was the big difference between radical and step growth. So remember that in step growth, this was described by Carosa's theory. It took a very long time and very high conversions to get polymers. For our anionic or our living polymerization, we start forming polymers or start initiating our chains. And then the longer we wait, or the more monomer is being consumed, the longer the polymer chains get, because all the polymer chains start to grow at the beginning, and then they add monomers. And that means that this relation between conversion and degree of polymerization is linear. Anionic or living polymerization. And of course, a linear relationship is always very easy to control, because you can simply say, I want to have this many monomers, this many monomers, this many monomers, and you get more and more material. Okay, these are the consequences for the polymers. And now to the grand finale. What we can also do is, just imagine we have monomers A, and we add monomer A, until all the monomers are consumed. Now our reaction is passive, because all the monomers have been consumed and there's nothing to polymerize. But this chain end here is still active. It still carries a negative charge. So it just waits for a new reaction partner to show up. Now think about, instead of adding more and more of the same monomer A to make the polymer chain longer and longer, we add a new polymer B, which I now draw in red. the polymerization will continue, and now all these B's will be polymerized. And let's say, well, we are getting very crazy, and now we add polymer C, which will also be added as a block. So what we create is block copolymers. Block A, block B, block C. So there's a possibility to chemically link polymers together to create block polymers. So now you may think, well, why bother? Now we have different polymers chained together, but now you can already just briefly imagine that each polymer has certain properties. If you chemically link different polymer chains together, then you combine the properties of these different polymer chains or of these different monomers within a single polymer chain. And this, of course, allows you to tailor properties very precisely, and if you want to create very interesting properties. And that is not the only thing. What we will discuss in the next lectures is that polymers do not mix very well. And if you have a block copolymer, it allows you to chemically force or bond together polymers that actually do not want to mix. And this generates very fascinating properties because if you want, you force the molecules in a situation where they do not want to be, and they try to phase separate and come up with very elaborate structures to avoid their phase of mixing. So block copolymers indeed is probably the most beautiful polymeric architecture for somebody that likes to self-assembly like me, because you give them an incentive to self-assembly into very intricate structures simply by chemically binding them together. And this is the beauty of block copolymers. And we can only make block copolymers if we have a living polymerization, because we rely on this active chain end here so that we can polymerize the next block and further blocks and so on and so forth. Okay, this is the important thing about a living polymerization. Now we've seen that anionic polymerization is very good at doing this, but it also has disadvantages. Now I've showed you a reaction that terminates an anionic polymerization, that is the presence of CO2. The presence of water terminates the reaction. There's different, generally speaking, I would say the presence of impurities will lead to loss of this living character. And that means it's very difficult to conduct anionic polymerizations. You have very active species, so you need to exclude all kind of oxygen, impurities, water, and so on, because otherwise your reaction mixture needs to be or will be destroyed, starts to burn or so on. And you need to be very careful in purifying your monomers in order to achieve these living characteristics. And everything is, if you want, experimentally relatively cumbersome. In contrast, radical polymerization is super simple. You take your monomer, you put them in a solvent, you add an initiator, and pretty much you form a polymer. This is why it's so popular and so easy, and so many products come from radical polymerization. It's cheap and easy to do. Anionic polymerization is not. So this brings me to the question whether we can maybe combine the best of two worlds and create living polymerization conditions from from a radical polymerization. So let me just show this to you on the blackboard. So it's ideal for living polymerization, but it really has these disadvantages that we have difficult experimental conditions, and also, of course, the choice of monomers is fairly limited because we always need to take care of having these electron withdrawing groups. In radical polymerization, we pretty much don't care. If a molecule has a double bond, it can be polymerized by a radical polymerization. So if we think about a living radical polymerization, what do we need to take care of? What is kind of the key problem? Now, how to make a radical polymerization living? And clearly, what you've seen is living characteristics come about when we can suppress termination reactions. So we need to suppress termination reactions. Now our problem, of course, is that the radicals tend to terminate very easily. If they find each other, they can always recombine. And this, to kind of alleviate these tendency to form polymeric or to form covalent bonds by recombination is not very easy. So the best chance we have is that we need to temporarily deactivate the radical. So we need to, if you want, hide the radical, and if it's hidden, then it cannot recombine. If it cannot recombine, then it remains living. And this kind of mindset is known as reversible deactivation radical polymerization, or maybe more commonly known as controlled radical polymerization. And now let's have a look at how this kind of almost philosophical concept can actually be translated into practice. And in order to do this, let's move back to the blackboard. And now see if we can do living or controlled radical polymerization. So the key principle for all these approaches is that we need to reversibly or temporarily shield the radical. And then we have two strategies. Strategy one, is to simply hide the radical. So this is reversible capping of a radical. And what I mean by this is that we have our polymer chain. Here's our radical, and here's a side group. And now we add something that can react with this radical. Whatever this may be, we can discuss this in a second. And they can now recombine. And now the radical is gone. And this, here, this is the box. It's kind of the placeholder. And this side of the reaction, if you want, this scenario, is called the dormant species. Because it's passive, it's sleeping if you want. And this one is called the active species. And while it's active, this radical can undergo a normal radical polymerization. So here we can add monomer, and the monomer will be incorporated in the chain, so the chain will become longer and longer. But as soon as this mysterious component finds a radical end, they will reversibly deactivate, and it will not be able to undergo either polymerization or termination reactions. And now what we need to do is we need to choose our equilibrium in a way that most of the species are in this kind of state. So typically the radical sleeps, cannot react, and every now and then this bond breaks, it starts to add a few monomer units, and then it goes back again. And why does this work? Why does this create living conditions? In this scheme, the number or the concentration of radicals is strongly reduced. And the concentration of radicals, if we look at our kinetics, then we realize, look at this, or this is what we did in the last lecture. If you want, you can look it up again. the rate of polymerization, so how fast the polymer grows, scales with the radical concentration, which is bad, of course, because if we decrease this, then the reaction will take longer and longer. So this is the negative side of this strategy. However, the rate of determination scales with the number of radicals squared, simply because we need two radicals to find each other. And that means that this reaction is very strongly suppressed. And if we suppress the termination rate very strongly, then we can achieve living polymerization conditions. Because at normal timescales, this is extremely unlikely. Because all of them are protected, they will never be able to find each other. And when it opens very quickly, it just adds a few monomers and then goes into hiding again. But as we said, the problem is that we also suppress our reaction or our polymerization rate, and it takes a longer time. Nevertheless, the gain is that we can make block copolymers using any monomer susceptible for radical polymerization. So this strategy here, if you want an analogy, would be in a football field. If the radical is a football, this would be either a player takes the ball and puts it under its shirt, and then it's gone, or the player passes the ball to the goalie, who then takes it up and keeps it in his or her hands. And for this, the ball is out of the game. No defense player or no offense player can attack the ball, and this is why you don't, if you want, get a goal scored, or in this case, you don't get a termination reaction. So on the football pitch, this makes it very boring. Here, it makes it slow, but as we said, it can increase the likelihood, or it can allow us to achieve living conditions for a radical. Okay, how does this work? Let me give you a brief example. Maybe directly here. So I need to clean up again, and while I do this, you can already think about what we can do to implement this strategy. So strategy 1. And this example is known as ATRP, atom transfer radical polymerization. And what we do here is we take advantage of metal complexes which can reversibly donate and take up an electron. And this electron can switch from a radical species to a dormant species. Let me put this, use metal complexes to manage electrons. Okay, so the idea is we have our an organic halide and this organic halide does not react, it's not a radical. So this serves as the dormant species. And now to this reaction we add a metal complex, metal, let's say N plus, let's say for example metal plus, and this has a certain number of ligands, for example chloride ligands or halogen ligands. And now during the reaction, this halide can be shifted to the metal complex. And again, we want to choose our complex in a way that mostly it's in this dormant state. But every now and then, this bond is broken. This metal atom happily accepts another electron along with the ligand, and it forms an active chain, a radical plus a metal N plus 1 plus and XN XN plus 1. So in case if it was a chloride, it would be XCN plus 1. So here now we have our active species, and this one here takes over the halide. So you see the electron along with the halide goes into the complex. Here now we can have our polymerization. But very soon the reaction will go into this dormant state again and is therefore protected from termination reactions. This is, I would think, the most popular way on how to do living or controlled radical polymerization following strategy 1. Okay, let's look at strategy 2. Now, if there's a 1, there's always a 2. Now, if you go back to the football analogy, this is the boring or, let's say, low-level alternative. Now, if I want to play on time, if I don't want to lose the ball, I pass it to the goalie picks it up, maybe goes down on its knees or her knees, and waits for time until he or she releases the ball again. A much more elegant way of avoiding the loss of ball is to simply pass it around all the time. Of course, you need to be a good football player so that you don't lose the ball, but generally, if you do this very well, think about traditional Brazilian football techniques, you never lose the ball because it always goes back and forth, and the defender will not be able to have a chance to get the ball. And this strategy translated into polymer science would be a rapid exchange of radicals. So this is maybe slightly less intuitive, but let me show it to you. Let's say we have a polymer species. That is currently active, and now we let it react with a second species that is passivated. Here's the passivation block. And now, while this is active, of course, it can undergo polymerization. But very often, these two react, and now the radical goes over here, this becomes active, and this becomes passivated. Now this is blocked, and this one is active. And while this is active, of course, similar to before, this can polymerize. And in this case, the radical is never lost. It just changes back and forth, more similar to the football that is being passed around. So the principle here is, now I'm running out of space, we exploit a very efficient chain transfer. Now, chain transfer, if you remember, means we have a radical in one chain, this radical terminates, and the radical goes to a different chain. And in this case, we make a reversible chain transfer that very quickly jumps from two polymeric species. Very efficient reversible chain transfer. And since this reversible chain transfer renders polymers from being active to being passive very quickly, you also suppress the termination reaction. Because the second radical will never find an active species because they quickly change back and forth. And the really important characteristic of this strategy, even though it's maybe a bit less intuitive, is that we actually do not change the number of free radicals. So in football analogy, the ball is still in the game. It's only that the enemy or the other team cannot get to the ball. Similarly, you cannot make a termination reaction very easily because it switches back and forth, but you still have the same radical concentration. It's here or here. And that means that you do not slow down the reaction. You suppress termination, but you do not slow down the reaction. That's, of course, very attractive. And let me give you one example of how this works. And for this, I think we need to clear up space again. So this example is known as radical addition, fragmentation, polymerization. Or short, raft. So what is the principle? We need to have something that mediates these quick chain transfers, and what we use is dithioesters. For example, such a compound. And we add this to our normal radical polymerization. So what happens in this case, let me just show you the chemistry really quickly. This is very good at accepting radicals. So this works as this addition agent. And similarly, it can fragment again to release the other side of the monomer or of the polymer. So we have a radical that reacts with this component, And it reacts in a way that this double bond is broken and the radical is bound here and the radical is transferred to the central carbon here. This is the benzene ring. Here we have our radical now, and this has not changed. And now the situation is of course also not very stable, and it can either back react, know that this bond is broken again and we recover this double bond, but the same can happen on this side, and this is why we need this dithyroester structure. So with equal likelihood, this can break, these two radicals combine, and we release a new polymer. A new radical. Now we have our dithyroester created on this side, and we release our, in this case, benzene radical. And now, of course, this can undergo polymerization and then will become a longer chain. And after a while, the reaction can go back. It forms this state again. The radical is captured by this dithyroester again, and it can break out in this direction and releases this polymer again. And then in the course of the reaction, it goes back and forth. Sometimes this side polymerizes, then the chain transfer kicks out this species, this polymerizes, and it goes back and forth, and at both sides the polymer grows and is being mediated by this dynamic chain transfer agent of the dithyroester. And in this way you create polymers with equal lengths, and since they continuously switch back and forth, if you have sufficient amounts of this dithyroester, the termination is very strongly suppressed. Good. Okay, so you see that even for something seemingly impossible, namely preventing radicals that are very active and very susceptible to combination from terminating, is actually possible, or at least maybe not completely possible, but efficient enough to suppress termination reactions in a way that we can achieve a living polymerization also with a radical type of polymerization. So you see this here on the slides as well. Here you have these two processes again. Here is the strategy 2. And here you also see in some more details, you can look it up in your slides if you want, how this Raft agent mediates between these two polymerizations. But again, you see here, polymer 1 reacts with Raft species where polymer 2 is bound. You have this transition state that can now react in both ways, and now it can kick out this one here to polymerize again. Okay, so this is the dynamic equilibrium that we see. Good, okay. So key steps: Raft agent added to a normal free radical polymerization. The rate of chain transfer to Raft agent is faster than the termination reaction, so it's always more likely to do a chain transfer than to do a termination. And that means that the free radical will be continuously captured by the Raft agent, and this makes termination less likely. Good. Final point for today is Ziegler-Natta catalysis, or the Ziegler-Natta catalyst. So I know this is a course for engineering students, and I know that engineers are very fond of catalysis, and for a good reason, of course. Catalysts typically save resources, make the world a bit greener because you reduce involved species and so on, heat, and be more efficient. And catalysis, of course, is also very important in polymerization reactions. This is not something that I have great amount of time to talk about. Just want to give you one important example of a catalyst that is really used in industrial processes at a very large scale to make polymerizations. So the point is that polyethylene is one of the most important commodity polymers that is pretty much used everywhere. And if you remember from last week, if we use a free radical polymerization to make polyethylene, then we will inherently end up having some amount of side chains. And side chains are never good because it prevents the polymer from packing very densely. And hence, what we produce if we do polyethylene from free radical polymerization is known as low density polyethylene. Now, if you hit stop and go to your whatever bathroom, to your kitchen, or wherever you have a lot of plastic materials and look at the labeling, you very often see HDPE on polyethylene products, high density polyethylene. And this is linear polyethylene. Now, as it turns out, you cannot do this by radical polymerization, but you can do this by a heterogeneous catalyst. And this reaction became so successful that it was awarded the Nobel Prize in Chemistry already a long time ago, but is still used in modified forms to make high-density polyethylene. And this Nobel Prize went to Ziegler and Natta for this development of this process. And what they use is transition metal halides and an organometallic component. And we'll go into details in a second. And this changes the way the polymer is formed completely. And this is known as an insertion reaction at the catalyst. And this, as we will see in a second, prevents side chain formation. Hence, we can make high-density polyethylene or HDPE. And as a short side note, if we don't use polyethylene, but if we use other monomers, then we will see that the polymers will become what is known as stereoregular. So the side chains, this X and Y, R1, R2, however you want to call this, will either always stick out on the same side or it will change alternatingly. This is maybe a bit the easiest to understand. If you have such a polymer, it has a much higher chance to crystallize because the side chain always point to the same side, so you get a much more ordered structure. And if you need to pack them into a crystal, you have a chance if you have such a configuration, but you do not have a chance to crystallize them if this is not defined. No, if X and Y can point in one direction or the other at each monomer unit, it cannot crystallize. And what we will see later in the lecture, whether or not a material crystallizes has a huge impact on the resulting product properties. So gaining control of this arrangement of the polymers is really, really, really important. Okay, so let's just have a quick look at how this reaction works. So as we said, this is a mixture of titanium chloride. This is the surface of titanium chloride. And we add an organometallic component. And you've seen organometallic components before in the lecture, combinations of, for example, in this case, aluminum and an organic rest, in this case, for example, ethyl groups. And what happens if we let these react is that this organic rest R, so for example, this ethyl group here, is being transferred to the titanium center. So you see it forms a complex, and then it chops out a chloride and leaves an organic rest. And this is now the active center for the polymerization. So what happens next? We have a titanium metal center here that has a free coordination site. And we have a molecule here that actually has pi electrons. So it can donate electrons to the titanium center. And it does so by approaching this titanium center via the double bond. So the double bond makes, if you want, contact with the titanium to share the electron or to form a complex, to share the electron density with the titanium. And why it produces something stereoregular is very simple. You have a heterogeneous catalyst, so there is a preferred orientation of this side group. Let's say the side group is much longer on one side as compared to the other, and there's always one side at the complex that is sterically more or less hindered. So either this can always point to the top or to the back. No, there's other things around here. And one of these configurations will have the lowest energy. And that means in the course of the reaction, and we come to this in a second, it will always approach at the same configuration. And if it always comes at the same configuration, in this case CH2 group sticking out to the front, then it will always form a polymer where the CH3 group is always pointing in the same direction, which is an isotactic polymer. Good. Okay, so what happens now? We have this double bond, and now it forms a bond or it inserts into this TIC bond here. So first it forms a cyclic transition state. You see this bond here, and these bonds are kind of converting, and now this bond between the double bond and the titanium is formed, and the bond between the titanium and this rest here is released. So now what you have is a free side on top here, and this R is inserted into your double bond, and the double bond is converted into a sigma bond. And now in the last step, the entire chain that is formed propagates back in here. And now what you see is that this chain became longer, and the binding site is free again. And this means if you repeat the same process again, you will have a new monomer approaching here. This will insert it again. So this chain will grow longer and longer as more and more monomer is fed at this free binding site. And if you do this over and over again, you form a polymer that grows out of the catalyst, if you want, to the top of the screen. And then what you need to do is eventually, when you terminate the reaction, you cap it. You can do this by adding hydrogen, for example, which in this case would be the termination reaction that releases the free polymer and saturates the titanium then with the hydrogen atoms. Very generally, just in very few words, just to show you that indeed catalysis can play a very important role in polymer science as well. And the Ziegler-Natta catalyst is of special importance because it can create linear polyethylene by this insertion type of mechanism, and it allows to form stereoregular polymers. And with this, I'm at the end of today's lecture. Let us take a few minutes to recap what we learned. First of all, we saw that vinyl monomers can also be polymerized via active species that carries ions, so either carbocations or carbanions, and this then leads to cationic and anionic polymerization. And you've seen that especially this anionic polymerization is very attractive because it can form polymers in a linear fashion. So that means the relation between the degree of polymerization and the conversion is linear. It allows adjusting the molecular weight very conveniently. It allows to make very long polymer chains. It allows to make polymer chains with very narrow size distribution. And maybe most importantly, you can make block copolymers. And then we discussed how we can make living polymerization using radical polymerization to achieve the same features. And we saw that the key there is that we somewhat need to mitigate termination reactions. And we can do this either by end capping or reversibly end capping our radical, or by doing reversible and alternating chain transfers. Okay, two different strategies having the same overall impact, mainly that termination reactions are strongly reduced. And then finally, we discussed a catalytic process that leads to linear polyethylene or stereoregular polymers, which is this Ziegler-Natta catalyst that operates via an insertion at the active catalyst center. And with this, I'm really at the end of my lecture. I thank you very much for listening and looking forward to seeing you again next week. Thank you.